Hello, everybody. This is Sumit. I hope you all are doing well during the crisis of COVID 19. Stay home, stay safe, and during that, let's study dynamic programming. This is also called DP as an abbreviation. So, dynamic programming is one of the most important topics in algorithms. It's a bit tricky to understand, but with practice, it becomes fairly easy. And this is also one of the topics which is most asked during interviews. So, let's begin. This is an algorithm design technique designed by Richard Bellman in the 1950s. The word programming stands for planning. So people get confused that maybe you'd have to learn some kind of a syntax or a new programming language. No, it's not that. It's just a technique. So dynamic programming divides the problem into subproblems, solves it, and combines the solution. Subproblems must have overlapping regions. We will see what this means in a bit. We typically apply dynamic programming to optimization problems. So optimization problems means that it could be either a minimization problem or a maximization problem. Such problems can have many solutions and each solution has a value. We wish to find a solution with optimal value. It could be minimum or maximum as I told earlier. We call such solution optimal solution to the problem. Remember, dynamic programming always gives the optimal solution. It should give the optimal solution. So with this definition, it's very confusing to differentiate between divide and conquer technique and uh, dynamic programming technique. Let's just have a look at it before we move forward. So divide and conquer technique divides the problem into disjoint subproblems. Yes, this is important. This is the difference. And it solves the subproblems recursively and combine their solutions to solve the original problem. For example, merge sort. This is an example of merge sort. You can see that this is an unsorted array and the final answer is the sorted array. So what merge sort does is it divides the problem, the unsorted array, into subarrays until it is no longer divisible. So the size of this is 1, as you can see, and later it will start combining, it will start sorting until you get the sorted array. You can look at this subproblem, it does not match to any other subproblem. And similarly, other subproblems are not matching. So all the subproblems are disjoint and there are no overlapping subproblems. In contrast, dynamic programming is applied when the subproblems overlap. Rather than solving these overlapping problems again and again, we typically store these results in a table, reuse them later on. This table that we have, we can then use to construct solution to the original problem. So we want to look at differences between greedy approach and dynamic programming approach as well. So greedy method picks the best choice at every stage, but for many problems, it may or may not result to globally optimum solution. On the other hand, in dynamic programming, we make a decision using previously solved subproblems. It is guaranteed that DB will give the optimal solution as it looks at all the possible choices before making a decision. So when you hear this term, this sentence that it looks at all the possible choices, you may think that this is a brute force approach. It is kind of a brute force approach, but it's a very smart and very well planned brute force approach, is what I would say. These are the general steps to solve a dynamic programming solution. First, you have to find a recursive solution or recurrence relation to the problem. Second, you have to find the overlapping regions. Third, you have to store the subproblem solution in a table or a matrix. We will look at all these steps with the help of an example. So this is Fibonacci series, and this is a series where every term is the sum of its previous two terms. So if you look at 5, it's the sum of 3 and 2. If you look at 13, it's the sum of 8 and 5. This is an index-wise representation of Fibonacci terms up till n. So if I want to find what is the 8th Fibonacci number, I should know what is 7th and 6th. Similarly, if I want to find 6th Fibonacci number, I need to know what's 5 and 4 and so on and so forth. So recurrence relation For nth Fibonacci term is fn minus 1 plus fn minus 2. The base case is f of 0 and f of 1. So the problem is to find the nth Fibonacci number. And we will solve this problem with recursion and dynamic programming. So recursion is defined as a function calling itself and it terminates on a base case. So you should know recursion because it's also used to solve top-down approach in dynamic programming. This is the program for Fibonacci number. This is the recurrence relation that we defined previously, and this is the base case on line number 3 and 4. The base case says that if n is less than or equal to 1, just return that number. So if n is 0 or 1, it will return 0 or 1 respectively. Before moving forward, people who are not comfortable with Python, I would want to explain a few things about it, especially what we are using here in this program. So def keyword defines the function. You would see that it doesn't have any return type, int, string, whatever, because Python doesn't care about it. Python is very indentation specific. So this block of code belongs to this function because it's indented. Return belongs to if statement because it is indented. And this is how Python recognizes which block of code belongs to which function or statement. So we make the first call. This call would generate fib4 instance of the code. When it comes to fib4, again it will call 1 first because the condition will not be met. Similarly, it will call 1. It will call 1. So now when you come at this as this instance of the program, we'll call fib1. Now this is the base case. It's supposed to return n. N is 1. 2 will execute and this is the base case. It will return 0. This instance of the program has finished both its calls and its job is to add both these numbers which it has got and return it to the calling function which was 1. That's n minus 1 for sure. Now this part has got a value which is 1. It will make the second call. This is again the base case. It's supposed to return n which is 1. Fib of 3 have finished both the recursive calls. So this will add these both numbers and return it to the calling function. This is left with the second call and we will have to recurse the whole tree like this. You can see that fib of 2 is supposed to return 1. So instead of traversing, I am just returning 1. Add these both numbers 2 and 1 and send it to the calling function. Similarly, this will also make its second call. Fib of 3 is supposed to return 2. So I'm not going through the whole tree. Add these both numbers and the answer is 5. So the fifth Fibonacci number is 5. Time complexity of this algorithm, recursive algorithm, is O to the power 2n. So the recurrence that we get here is twice of t n minus 1. Why? You can take, instead of taking t of n minus 2, I'm just making it t of n minus 1 for easier computation. And when you solve this recurrence relation, you'll get 2 raised to power n. This is an exponential time complexity and it's very expensive, very, very expensive, and we would like to reduce it. Space complexity is O of n. Space complexity of a recursion is defined by maximum height of the tree, and you can see the maximum height is n. So space complexity is O of n. One thing worth noting here is this program is doing a lot of recomputation, a lot of rework. You can see I have colored fib of 2, all the repeating substructures with the same color. So fib of 2 are of the same color, fib of 3 is the same color. What dynamic programming does, it will save this recomputation so that next time fib of 3 is called, it already has the answer. It just has to look up like a caching mechanism and give the answer. And it can save all these extra calls. Let's see. So dynamic programming stores the results of expensive computations and return the stored result when the same input occurs again. There are two methods to do this. One is top-down approach, which is also called memoization. Please don't confuse this with memorization. I have not made a spelling error here. And the second method is bottom-up approach. It's also called a tabular approach. We'll look at this. So in top-down approach, we have the problem and we are dividing into the smaller instances of the problem and then trying to solve it. While we are solving it, we store it into a table, and whenever a similar call is made, we will return the value which is already computed in the table. So let's see how this works. Okay, this program is very much similar to the previous program. The only difference that you can find is the extra variable t. This t is the array, a 1D array which stores the computed results at every step. It will only store once. T is initialized with -1 in the beginning. -1 will tell us that the result is not computed, and so we should make further calls. So line number 3 and 4 in the program will help us save the computation. What it does is, if it has a negative value, then the condition will fail and the program will go to line number 6 and make the recursive call. But if we already have any saved result for the value of n, this is supposed to return the saved result. So let's see how this program works. So I'm trying to find the fifth Fibonacci number. I call fib of 5. T of 5 is -1. This condition will not be satisfied. It will make this recursive call. Similarly, we have -1 until the index value 2. So the first call will have to be made. Now this will call the base case and this is supposed to return t of 1. T of 1 has 1 and t of 0 for the second call, t of 0 is 0. Add it up. After adding, we have to set this value at t of 2, which is 1, and send t of n, which is 1, to the calling function. Now I'm on the instance fib of 3. I'll make the second call and this is the base case. It will return 1. Add it up on index 3. Add the result. Result is 2. And send 2 to the calling function. Now see what happens. It will make the second call and it will call fib of 2. It will check, is t of n, t of 2 greater than 0? T of 2 is greater than 0. It's 1. Send the result. Add the result to the table and send the result, which is 3. You can see that this whole call is not made. Similarly, this function is supposed to call the second call, fib of 3. We will check what value do we have for fib of 3, and fib of 3, 0, 1, 2, 3 has the value 2 stored in there. Add this up, store it in the table, and the value, return that value. So fib of 5 is 5. You can see that the result matches. So this is a top-down approach. Usually when you have to visualize, top-down is easier than bottom-up, but bottom-up is computationally better than top-down approach, and we will see that in the end. Let's analyze the time and space complexity. The time complexity of dynamic programming approach revolves around how you fill the table. So we have filled the table just once and then we are reusing it. So time complexity is O of n. The space complexity is also O of n because of this array. Let's try to solve the same problem with the bottom-up approach. In bottom-up approach, we look at the base cases first. So we already have the solution, which is the base case, and we build up progressively until we reach the final solution. Let's look at it. Before moving forward, I will explain how the for loop works in Python. So I will take the values from 2 to n. So in this range function, it excludes the last bound. It takes one less than that. So it will go from 2 to 5 because n is 5 here. This program is also pretty much similar. This is the initial state of the table, and I'm running it from 2 to 5. This is the index from 2, this is index number 2, and this is index number 5. What we have to do is just keep adding the previous two numbers and store the result here. This is what this line is doing. 1 plus 0 is 1, I goes to 3. 1 plus 1 is 2, I goes to 4. 2 plus 1 is 3, I goes to 5. 3 plus 2 is 5, and the program ends. So this is the final state of the table, and you return Tn. T of n is 5. This is bottom-up approach. It's very much simple. Time complexity is O of n as we go until n just once. We have only one for loop. Space complexity is O of n because we are using the array to store the values. You can see that we are only making use of the last two values. So there is one more improvement that can be made to this program. What if we use just two variables and we can improve the space complexity to constant? This is the final optimized version of Fibonacci problem, and it's Fibonacci number. Here we have two variables, final and temp. After every iteration, temp value will go to final and temp will hold the next Fibonacci number by adding final plus temp. You can see this in the table here. So initially final had the value 1 and temp had 0. After 0th iteration, final got 0 and temp has 1. Similarly, temp holds the next Fibonacci number and it keeps exchanging with the final variable. And in the end, we return final. The time complexity of this algorithm is O of n because we have to go until n. We have one for loop. Space complexity is improved. So you can see how we went from exponential time complexity to linear time complexity and how we improvised on space complexity as well. So let's see how these programs behave. Previously, I told you that we should prefer bottom-up approach than top-down approach. And let's see why. So this is a recursive function trying to compute fib of 30. You can see it took a little time. This is pretty much instant. Bottom-up would be pretty much instant. So is the final optimized version. Okay, now let's try to compute fib of 5000. So it throws an error, and the error is maximum recursion depth exceeded in comparison. So this is the problem with recursion. Let's try to compute it with bottom up. It's a pretty big number, but no problem. Similarly, this will also have no problem. Let's do 50,000. It will do it. Okay. So that is it. If you like this video, give a thumbs up, subscribe to my channel, and I'll see you in the next video. Bye.